So our first class will be on the introduction of the power electronics, and we're going to also look into the semiconductor devices. So this lecture will, inshallah, will cover the first course outcome. Before that, I'm going to read the course outcome of the power electronic course, which is the number one, which will be the describe the characteristic of power switching devices and their drive requirements. Course outcome number 2 will be evaluate the operation of power electronic converters. And finally, number 3, simulate various converter circuit topologies and control strategies. So we're going to cover this course outcome. Number 1, which is describe the characteristic of power switching devices and their drive requirements. So I hope you already download the monograph, right? So chapter number 1 will be the introduction, as well as the we're going to discuss chapter 1 and chapter 3, and I will start with the introduction to power electronics. So what is a power electronics? It is, of course, a field. It is a field of a branch or a branch of electrical engineering that deals with the application of power semiconductor devices for the control and conversion. This is the key word, for the control and conversion of electric power by supplying voltages and currents in the form that is optimally suited for the load. So we know that we in the power system we can have the voltage and current in the form of AC and also as well as the DC, and it depends on the availability of the input, the source, the supply, and the type of current or voltage available from the input, and also the requirement from the output side. So now we have this input source, and on the right hand side here we have this load, which is the output, which also can be from in the form of AC or DC. So somehow you need to have this power electronic converters, so it can convert from AC to AC with the different level of output AC. You can also convert from AC to DC in the case of rectifier, or otherwise we have the DC to AC in inverter or DC to DC with a different level of output voltage, right? So this is the basic block diagram. If you look at this figure 1.1, this is the basic block diagram of the complete. This is a complete power electronic system, whereby you have the input, the output, and the power electronic converters, as well as the controller. This is a feedback controller system, so that you can regulate, you can maintain, you can control the output voltage, because we know that the input source normally it is maintained at a certain value, is unregulated. It actually maintained at, for example, at the end before single phase supply we have a 240 volt RMS input. If you have a three-phase system, then you have a 450 volt RMS line to line voltage. Okay, and for EPO 510 we only discuss on the power electronic converters. We're not going to cover the controller system, okay? The feedback control system here. This is beyond EPO 510. Probably later in the next semester we're going to have electric drives, then we possibly will look into the controller circuits here, right? So that is very electronic converters. And now we look to the goal of electronic power conversion system. So while doing these conversions, there is an ultimate goal of electronic power conversion system, whereby we want to convert the electrical energy from one form to another, which is from the supply to the load, with the highest efficiency. It's a key point again: highest efficiency, high availability, and high reliability, with the lowest cost, smaller size, and weight. Right? So in order for you to design a power electronic conversion system, we need to take care or to consider the efficiency, the variability, the reliability, as well as the cost, the size, and the weight, because it is not applicable or practical if you use a component or circuit that do the conversion but with lowest or low efficiency level, right? And what about the high availability? You use the components which is not available in the market, so it is a waste of time for you to get the components, the availability of the components. So that also needs to be considered, as well as the reliability. Kau boleh percayaan, which means you want to make sure that your system, your circuits works as long as possible, isn't it? It is not meaningful if you design a very high system, high efficiency system, and it is a high availability but with low reliability, which means you can only operate 10 minutes, for example, and then the converter gone, probably gone. It only works for 10 minutes. It's not worth, is it? So you need to make sure that your system also has a high reliability, and finally make sure that it is a lowest cost, small size, and weight. For example, if you design a power supply for the aircraft, so you need to make sure that it is small and of course lightweight, isn't it? Okay, so that is the goal of electronic power conversion system, and this is the conversion concept of the power electronic. We take uncontrolled rectifier, for example. All right, so we know that the supply TMB can have a 240 volt RMS with a 50 Hz frequency, and 340 volt is the peak value. So 240 multiplied by square root 2 will give you the 340 volt. But a customer needs, for example, a DC voltage for a welding purpose, for example. So you need to make sure you need to convert that 240 volt RMS with 50 Hz into the DC voltage required by the output. So for TNB, sine wave supply gives 0 DC components. So if you deliver that AC voltage to the output, of course, if you look at the DC or the average value, DC component is always the average value of the waveform or the supply or the voltage. So if you take the average of the sinusoidal waveform, of course, you will get the 0 level, isn't it? It will give you 0 DC voltage. Right? So how can we get a different level of output in the form of DC? So we use this half wave rectifier. This is known as a half wave rectifier. Whenever you use the diode as the device to convert the AC waveform to the DC. So if you look at this circuit, simple circuit, I think when you learn about the electronics, you came across the diode and its applications, and you know what is a rectifier. So for the half wave rectifier, during the half cycles of the supply voltage, you know that the diode is forward bias, and due to the resistor is a purely resistive load, the current start to flow in that direction, isn't it? It will flow in that direction. Therefore, this is turned on and it appears as a short circuit, isn't it? So it appears as a short circuit, and therefore V out will be equals to V in, the TMB, the voltage from the supply. So if you look at this waveform, this is a supply voltage, V in, or Vs. So the output voltage will copy exactly the input voltage during the first half of the cycle, but when in the negative half cycles, the diode will be reverse bias, right? So now in the negative half cycle, this is known as a negative half cycle, the diode will be on the reverse bias and current start to flow in that direction instead of start to flow. It tends to flow in that direction, isn't it? The opposite way. So therefore it will be against the arrow of the diode, and therefore the diode will be off, turned off, and therefore it will appear as a open circuit. So this is the diode here will appear as the open circuit, and therefore there is no current flow. Therefore voltage, output voltage will be equals to 0. So there is no current flow, output voltage will be 0. So therefore if you look at the waveform again, so you will copy the supply voltage half cycle, positive half cycle, but during negative half cycle it will remain 0, the output. So this is your output voltage waveform. So with this output voltage waveform, then we can find the DC voltage or the average voltage, and this will be viewed by the load as a DC voltage, and therefore you can get the DC voltage at the output. So how to get the output voltage, the average of the output voltage? You need to apply this equation, which is you integrate, this is general equation for any waveform to get the average value. The general equation to get the average value, you integrate the waveform full cycles, which is from that to the point, and this is your T, is it? This is T from there to there, this is your period, and integrate that. VDC T is the equation for the waveform, and you divide by the period 1 over T, so that will give you the average value. So integration is actually the area under the curve, isn't it? So when you look at the waveform again, convert that into radian, 1 over 2 pi. We know that T equals to 2 pi in radian, so the integral also goes to 0 to 2 pi, and then the voltage, and then when this is still the refer to the equation of the waveform, but when you zoom into this particular waveform, it only exists from 0 to pi, isn't it? So this is your pi, and this is 2 pi. So the waveform only exists for 0 to pi. Integrate, and this waveform is actually the sinusoidal waveform, V peak. So we have the peak value here as a V peak with a hat sine theta d theta, isn't it? So this is the equation, the limit from 0 to pi. So when you do that, solve that equation, then it will give you this output voltage VDC, the average value, equals to V peak over pi. Right? So here the output voltage cannot be controlled, uncontrolled. It only depends on the value of V peak as a supply voltage, and normally it is maintained at 240 volts. So therefore the output voltage here is uncontrolled, and that's why this is known as an uncontrolled rectifier, because we use the diode here. So how to make it is controllable? To control the output voltage, then we need to change the diode to the thyristor. Now the components that we use, or the device that we use, is the the thyristor or silicon control rectifier, whereby you have an extra terminal here, which is the gate signal. You can trigger, so the gate signals here will trigger the turn on, or these give us signals when to turn on the diode, the thyristor. Okay, so there will be a delay of the thyristor to turn on until it gets a signal from the gate signals here, gate terminals here. Okay, so for example, in this waveform, look at that. This is the gate signal, correct? And alpha is the firing angle when you start to fire the thyristor. Right? So until that point, then you start to trigger the thyristor. So from the if you refer to that particular zero crossing of the voltage to the half cycle, the positive half cycle, the thyristor is already in the forward bias, but since there is no gate signal, the thyristor there has not yet been turned on. So it still remain as an open circuit, okay, until you trigger the thyristor at alpha. So you have to measure what angle is this, okay, what angle of that. So alpha can be quantified by the angle, degree or radian, and until that firing angle is being triggered, then you can see the output voltage. The thyristor is on, and therefore output voltage will be equals to supply voltage. So now if you look carefully at the beginning, the output voltage is 0 because there is no current flow, and until you have alpha triggered to the thyristor, then you can see that the output voltage start to copy the input voltage here. So it goes until that point. So this is the output voltage, and during negative half cycle it will operate as the diode. Whenever you see that this is a reverse bias and the current start to flow in that direction, the diode, the thyristor here open circuit again, will open circuit, and therefore there is no current flow. Output voltage equals to 0. So therefore you see a 0 voltage here. Okay, so it only appears as a 0 voltage. So that will be the output voltage. And if you look at the waveform, this is the output voltage, and if you integrate that, if you get the average value, now it start from alpha. Your output voltage waveform start from alpha to pi, with that equations here. Okay, so now you have 1 over 2 pi instead of 0. Then now it becomes alpha to pi instead of 0 for the diode, but since we have the thyristor, then it becomes alpha to pi, right? So if you complete that evaluation, then you can see that the derivation, the output voltage now is no longer V peak over pi, but it is a V peak over 2 pi 1 plus cos alpha. So you can control the output voltage here by means of controlling the alpha value, isn't it? Yeah. So if you refer to the waveform again, as alpha is increased, then you can see that the output voltage becomes smaller and smaller. So if it's from there to there, for example, then you can see that the output voltage become smaller compared to alpha here. So let's say this is your alpha 2. Now your output voltage is smaller compared to the alpha, the first alpha that we introduced. Right? So that is a control rectifier, and that is known as a control rectifier, whereby you use the thyristor instead of the diode. Okay, next look at the application of power electronics. So generally there are two applications. One is a static application as the converter, DC-DC converter, AC to DC rectifier, DC to AC inverter. Mainly this is for the power supply applications. So this is known as static application. It involves non-rotating or moving mechanical components. So but whenever you use it for the drive, for the motor, then it known as the drive application. So it apply in the drive application. So next semester, in semester 6, you're going to learn about electric drives. Then you will see this drive applications a lot. Okay, variable speed drive system. So this is your power electronic converters, and it involves to motor. So you need to control the output, the motor, and therefore you have to sense the output voltage, sense the speed, and that will go through the feedback system, and you change the circuit controller, change the component, the device, the switch, therefore you can increase or reduce the motor speed. Okay, so two basic applications: static application and drive application. And this is other specific applications. So other specific applications for UPS, uninterruptible power supplies. In server, we normally use this UPS. And then power generation, transmission, HVDC in the locomotive train. Okay, electric train, we use this HVDC. And DC power supplies, transportation, in electric car, how you can call it to the battery. You want to charge the battery of the car, then you use this powertrain. Again, process control, electroplating, heating, and as well as security related applications. Okay, so why the current issues related to powertrains? Some energy scenario, of course, you need to reduce the dependence of fossil fuel. We know that the fossil fuel, which is the coal, negative, the natural gas, as well as the oils, becoming less and less, and we have to. The nuclear power is not feasible. Depletion of these sources is expected, so you need to move away. Move to the alternative source, for example, solar, wind, fuel cell, and etc. So this needs the conversion, powertrain conversion. And the rest read it. And then we have environmental issues, nuclear safety, as I mentioned earlier, nuclear safety, and then the burning of fossil fuels create global warming. This is some serious issues regarding the current power system generation, and that's why we must move to the powertrain. And this powertrain growth. What happens in the powertronics world? We have the advances in power semiconductor devices. There are actually a new device, emerging device, but we're not going to cover that. There's many, I can't remember, many more new devices coming up, which offer a high power capability with low power loss, for example. New ideas and control algorithm, demand for new applications, and of course, powertronic is an interdisciplinary field. It integrates many disciplines in there. For example, you have a power and energy for the conversion, digital analog electronics. To control the device, we need this digital analog electronics, as well as the microelectronics. You need to apply the control system in the controlling the output voltage. Computer simulation and software. Before you construct the circuit, you develop the hardware, you must go through the computer simulation. In powertronic, in EPO 510, we also have this cost outcome number 3, whereby we're going to use a PSIM. I have explained you yesterday on the use of PSIM to simulate the circuits. Right, so this simulation actually replicate, or it gives you some preparation for you to prepare for the actual hardware implementation. Okay? So this is a very good way to assess the performance of your circuits, whether it works or not, what sort of a power level that you will have. So you use this computer simulation software, and it involves solid state physics and devices, the research on the device as well, and then packaging, heat transfer. Since we're going to deal with a power loss, we also need to make sure that the power, the energy loss is converted or is moved away from the MOSFET, from the device, by means of the heat transfer system, which is normally, that the heat sink, isn't it? You heard about the heat sink. So this is the purpose of heat sink, which is we want to remove the heat generated by the device due to the losses in the device. Okay, right. Next is I'm going to jump that review of basic electrical concept. I hope you read this, and we're going to come again, cover this basic electrical concepts again when we discuss on the converter, on the single phase converter later on. Right. So we skip chapter number. Okay, overview of power semiconductor devices. Right, so we know that the power switches are the workhorses or the backbone of power electronic system. All the power electronic circuits must have these power switches, um, and it works in two states only: fully on or fully off. Fully on when the device conduct the current, and fully off when the device block the current from flowing. Right, so on and off. So that is ideally the ideal two states of the power electronic switches. So it can be categorized into three groups. There are three groups of power devices. The first one is the diode, which is the uncontrolled device. It depends solely on the control of the power circuit only, which is the voltage and current of the power circuit. It will turn on when it is a forward bias and the current follow the direction of the arrow of the diode, and it will be off when it's a reverse bias and the current also reverse direction of the opposite direction of the arrow of the diode symbol. Right, then we have this thyristor or silicon control rectifier. So for thyristor, it is also known as the half control devices, whereby you can only control the turn on of this thyristor, and after it turns on, it latch, it will keep on conducting the current until it will behave like the diode after that, whereby it will follow the, it will wait for the output voltage to be reversed, and then the current also reverse, then it will turn off. Okay, so for thyristor is a half control device whereby you can only control the turn on of the thyristor. And finally, the third group is the controllable switches. For the controllable switches, you can turn on and off at any times. All right, you can trigger the device at any time, and you can also instruct the device to be turned on at any time. Right, for example, the MOSFET, the IGBT, the BGT, as well as the gate turn off thyristor GTO. This is a new device. Right, so for we go to the power diode. It is known as a power diode because the voltage and current level of the diode is high. We can also have very small device or diode rating for 5 volts, 12 volts. Okay? But when we talk about these power electronic devices, it is more on the power diode, which has a high voltage and current capability. All right. So for the operating principle, I think we have you have covered this during your electronics subject. So when it diode is the forward bias, it conducts current with a small voltage forward, which is VF. Normally it's 0.3, 0.7. Germanium, silicon type of diode, they have this forward voltage, right? And this is the current or VI characteristics of the diode. So you have anode, one terminal, and the cathode at the other terminal, and this is the symbol of the diode, and the current will flow in the direction of the symbol to make sure that the diode is on. And during negative half cycle, it also have this avalanche breakdown here. If you apply a very high reverse bias voltage, it will break down, right? And this is the positive V and I current. So this is a VI characteristic. When reversed by negative, small leakage current flows until reverse breakdown occurs. You should not reverse. Okay, you can read that. And there is also, when you talk about the diodes, you have to also look into the reverse recovery time. The reverse recovery time. So during the turn off of the diode, they have some small times allows for the minority carriers to be swept away from the PN junction. Then you can make sure that the diode is off. So this is known as a reverse recovery time, TRR, and this is important in the designing the circuit, electronic circuits. So this TRR also actually determine how the range of frequency that the diode will be operating. Okay? So so normally if you want to use or apply the diode in the high frequency system, the TRR should be small enough to cover that. Alright, now types of diode. For the types of power diodes, we have this line frequency, which operate at 50 Hz frequency. Line frequency normally refers to 50 Hz or 60 Hz, a very low frequency, the normal mid frequency. Right? On state very low, large TRR, look at that, very high current, and normally it is a very high current and voltage used in line frequency applications such as rectify. Some applications of these diodes are battery charging, the supply, and so on. And there is also a fast recovery diodes. When you operate the circuit at high frequency, you must choose the diodes with have the capability of fast recovery diode. It be characterized as the low TRR. It also have a very small, low voltage rating compared to the line frequency diodes, and current rating array will be from 1 amp to several thousand amperes, not as high as the line frequency diode. Normally used in high frequency circuit for choppers. This is a DC-DC converter, and the other name for the choppers is the DC-DC converter. And power supply, and we also have the Schottky diode. Right, Schottky diode, it has a very low forward voltage drop, 0.3. It does also have a fast recovery time. It can operate at a very high frequency but low voltage drop. This is more preferable because the voltage drop determines the loss. Right, the higher the voltage drop, the higher the loss that the diode will have. So we have to have the Schottky diode. Of course, it's with more expensive compared to the normal diode, isn't it? Next is we have this thyristor. So for thyristor, we have an extra terminal here, the gate terminal. It works as the diode, but you have an extra function of gate signals here to trigger the diodes. Okay, so it is also known as a silicon control rectifier. Thyristor can only be turned on with two conditions. The device is forward blocking state, so you must to make sure that the thyristor is on the blocking in the forward, or we call it as a forward bias, and you apply the gate signal. Then you can turn on the thyristor. And once conducting, the anode current is latch, and then when it reverse bias, then it operates like the diode. Okay. So when the peak reverse high and you can read it in the forward bias mode with no current trigger, it exhibits a leakage current if the forward bias. So it works as the diode after it turns on. Right? So you will wait for the voltage to be reverse bias and the current to flow in the opposite direction of the symbol, then it will be turned off. So thyristor conduction, look at this. We have discussed that before when you look into the thyristor application of half-wave rectifier here. This is a half-wave rectifier. We have look into that. Okay, thyristor cannot be turned off by applying negative current. It can only be turned off if IA goes negative reverse. This happens when negative portion of the sun wave goes through. Okay, and when the current here goes to negative during that time, when the current try to go to the negative cycle, then it will be turned off. Okay, all right. Types of thyristor, we have a phase control, inverter grade, and light activated thyristors. And also we have this triad. So the triad is actually combine two diodes connected in back to back. For example, you have this two thyristors, but it combines in back to back connection. Alright, and this is known as triad. It always have two thyristors in it. Yeah, and you apply only one gate signal, and that signal will also control this transistor. Yeah? So this is known as a triode. Okay, now we jump into the controllable switches. The controllable switches, as we know, you can turn on and off by relatively very small control signals. It operated in saturation and cut-off modes only. There's no linear region operation, and power transistors do not operate in latch mode. Traditional devices of BJT, MOSFET, IGBT, as well as GTO. But now when we talk about high frequency, we're going to use the MOSFET. But if it's not so high frequency, we use this IGBT. BJT is less used currently, more on the IGBT as well as MOSFET. Okay, and we also have these new devices, gate control transistors. Okay, so we look into the BJT. I think this is very familiar IV characteristic. So normally we operate in that region, isn't it? So that's why we just now it works at saturation level area. Right? It works at that saturation levels. When you increase IB, then you can see the increase of IC. Yeah? So you have collector, base, and emitter. Yeah? This is bipolar junction transistor. So look at the rating of the voltage. It can be only up to 1400 amps, switching frequency up to 5 kilohertz. So it limits by the frequency of 5 kilohertz only, 5000 hertz. Low on-state voltage to 3 volt and the rest. Not popular in new products. So it's no longer popular in the new products. And this is the characteristic of BJT characteristic. You can, I think this is a familiar BJT Darlington pair. When you connect the first BJT to the second BJT, okay, and this IC equals to the IC here equals to the IC plus IC2 and the rest. So this is some equation here. The total gain equals to beta 1 plus beta 2 plus beta 1 multiplied by beta 2. Okay, then we move to the MOSFET. This is also MOSFET, but now the terminal is different. We have drain, gate, drain, and source. Instead of base, collector, and emitter, it has a gate, drain, and source. Okay, again, it works in that area. Ratings 500 volts into 300 amps, but now look at that, very fast device. So if you want to use for very high frequency, then you might go to the very fast device, MOSFET, but the voltage and currents cannot be very high. The applications cannot be for the high power. So there's some limitation. You can work very high frequency, but not so high on the voltage and current. So this is a MOSFET characteristic. Turning on of the off is very simple compared to the BJT. Only need provide the VGS turn on, gate source turn on voltage, and but it has a problem of RDS on instead of forward voltage. For MOSFET, it has this RDS on. When you turn on the MOSFET, then there is a small resistance exists during the turn on of the MOSFET. So I squared R will introduce the losses. I squared R will introduce the losses. Dominant high frequency application because application is in switch mode power supplies. So this is insulated gate bipolar transistor IGBT. Combination of BJT and MOSFET. Now you have collector, gate, and emitter. So this is IGBT. You have gate instead of base, but you have this collector and emitter to follow the BJT, and that's why it's known as a insulated gate bipolar transistor. So when you refer to the IGBT, it can work up to not so high. I mean, just before the MOSFET in the range of 100 kilohertz. Then you can use the IGBT. And then we have a gate turn off thyristor. It's not very popular yet, so you can read that. And next is on the driver circuit. So that is basically the three types of device. We have the diode, which is uncontrolled device, and then we have half control device, which is the thyristor, and finally the controllable switches, the MOSFET, IGBT, the BJT. So three types of MOSFET. So in order for you to trigger to switch on those devices, we need to have this driver circuit. You just like your light, for example, you need the switch, and how to trigger the switch is you use your hand, isn't it? So that your finger, your hands, your finger is the driver circuit. You must have this driver circuit to turn on the switch, right? So why? Because the control circuit here normally it has a very low current and voltage, but the power switch normally use a 15 volt and higher current for it to be turned on. Therefore, you need to have this intermediate circuit, the in between. So there is another circuit that because this to step up the voltage and current so that it will turn on the switch. Right. Okay. So it is an interface. It's known as interface between control low power electronics and high power switch. And the function is to amplify control signals to a level required to drive power switch, and also provides electrical isolation between power switch and logic level. The complexity of driver varies among switch. Most switches are simple compared to GTO, right? And this is an example of the how you can control the MOSFET. Gate drain source. Okay, so we use this optocoupler. LM311 is the simple amplifier. So optocoupler is a simple amplifier here, and then you just connect this point to the 15 volt voltage. This is a 15 volt because this VGS requires a 15 volt voltage for it to be turned on. All right, so you connect that with a 15 volt voltage. Now you have this LM311, which is a single amp with open collector Q1 to control the circuit. So when the Q1 is on, which is the Q1 high, the signal is high 1, it will appear as a short circuit, and therefore this point will be so this point will be connected to ground, isn't it? And therefore VGS will be equals to 0. MOSFET will be turned off. Okay, but when Q1 is off, so it appears as an open circuit. So between that point and that point is open circuit, and therefore you can see that this is a voltage VGG connected to here, there, and there will be a current flow to that voltage, the circuit through the gate signals, gate terminals, and therefore the MOSFET here will be turned on. So this is the simplest example of the driver circuit. For the thyristor here, we use this pulse transformer again, so that you can give a high current here to trigger the anode and control the thyristor. Yeah, all right. And one more thing, we also need the electrical isolation drivers. We use the optocoupler so that you want to maintain or you want to protect the control signals, because if you look at this circuit, you must protect this control circuit, because this is very crucial signals. This actually tells when to turn on. But if you mess up with this control circuit, of course the operation of the switches will not turn on and off in the way that we want it to be. Okay, so you must protect that. So how to protect that? We use the isolation optocoupler isolation device. This is optocoupler. So there is no physical connection between input control signals here to the driver side. So it will somehow protect the control signals. Okay, so this is some switches comparison, and this is actually a long time ago. Probably you can update the table here. This is a comparison between thyristor, BJT, MOSFET, GTO, and IGBT. And if you look at the voltage ratings, look at that. Okay, so GTO thyristor can operate at very high voltage, and look as well the current ratings. Right, 400 amps for BJT. GTO can go up to 5,000 amps, but the MOSFET only goes into 200 amps as well as 1.2. So this is the three important items that you need to look at, right? The voltage rating, current rating, as well as the switching frequency. So MOSFET can work at high frequency, 1 megahertz range. IGBT can go up to only 100 kilohertz. BJT 5 kilohertz. GTO 2 kilohertz. And thyristor is only for line frequency. Thyristor only work for 50 hertz or 60 hertz frequency. So that is switches comparison. And sometimes there is a question that need you to choose to select the best device that can be used for this application. For example, an inverter for the light from the locomotive, light rail train, LRT locomotive operating from a DC supply of 750 volt. The locomotive is rated at 150 kilowatt. The induction motor is to run from standstill up to 200 with power switches frequency up to 10 kilohertz. So the best way is to use the BJT, for example. A switch mode power supply for remote relay, the input voltage obtained from a photovoltaic PV produces a maximum voltage 100 volt, maximum current 200. The switching frequency should be higher than 100 kilohertz. So we use the MOSFET. Okay, so here you can use the BJT, and here you can use a MOSFET. The rest is HVDC transmission system, transmitting power of 300 milliwatt, system 200 link, voltage operating. So you can use the thyristor or GTO. Okay, so this you can use the thyristor. Right. Okay, now we move into the power switch loss. Okay, for power switch losses, as I mentioned earlier, when the goal of power electronics conversion is you need to have a high efficiency, isn't it? So when it involves the losses, these losses actually converted into the heat, the energy losses, and we need to have a high efficiency. Therefore, we need to consider the loss in the switch. So power switch losses, it is important to consider losses of power switches to ensure that the system operates reliably under prescribed ambient conditions, and so that a heat removal mechanism can be specified. Losses in switch affects the system efficiency, of course. So if a power switch is not cooled to its specified junction temperature, the full power capability of the switch cannot be realized. Derating of the power switch ratings may be necessary. What does it mean? Derating is, for example, a MOSFET, which can handle that the maximum of, for example, 2000 volt, for example, or 2000 volts. But because of that losses, it creates a heat in the device. So if you do not move transfer the heat outside of the device, the rating of that 2000 volt now is reduced to, for example, 50% of it. Instead of 2000 volt that it can handle, now it only works at 1000 volt. So of course the power switch losses issues is quite a main issues in the designing the power converter circuit. So what are those power switches involved? There are three main losses, which is the forward conduction losses. This is the loss that exists during the turn on of the switch. Then we have a blocking state losses, which is the loss that occurs during off state of the switch, and the other one will be the switching losses. This is the intersection, we call it the the transition between on and off off and on. There is a switching loss in between that. So there are those are three main losses. First, we look into the forward conduction loss, on state losses. Okay, so ideally we know that when the switch is on, it actually appears as a short circuit, isn't it? So there will be no current or no voltage drop across the switch, right? However, for the practical switch, there is still a small on voltage during this turn on. We will turn on voltage, and therefore I multiplied by V will create a voltage drop, and this drop contributes into the forward conduction losses. But for real switches, you can read that have forward conduction voltage between 1 to 3 volts. So and for the MOSFET, it has the RDS on. So when it's turned on, there is a RDS resistor here. There is a resistor RDS on, so that I squared R also contributes to the loss. Losses is measured by product of voltage drop cross V on I on average over the period. Forward conduction loss is the major source at low frequency. So at low frequency, the main loss is due to the forward conduction loss. Okay, that's only happens in the low frequency. But if you operate at a high frequency, this forward conduction loss can be neglected. Okay, so next is we have this blocking state losses. So for blocking state losses, of course, when it is turned off, the switch operates as an open circuit. Therefore, there will be no current flow, isn't it? Off state, open circuit, no current flow through the device. But in practical, there is a small leakage current. So that small leakage current multiplied by the voltage across it, that will create the turn off losses. And if you read it, hence the turn off knob value very small, can be neglected. Right, and finally, the major losses actually come from the switching losses. So ideally, if you look into the transition of current from the transition of a device from on to off and off to on, we can see that by ideally, when the voltage is when the switch is on, this is during turn on, isn't it? When you turn on the switch, the voltage drop to zero, isn't it? Because the switch will appear as a short circuit, voltage across it will be zero instantaneously. This is ideal case, and current now start from zero, and it jump to the circuit current I, whatever I is. Okay, and therefore there is no, in ideally, this is ideal practice, there's no overlap of voltage and current, because it happens in instantaneously. Yeah, a step change of voltage from voltage off to zero, and we have a current of 0 to the circuit current of I. So there is no overlap. However, for the real or practical switch, there is a slight delay, the transition of voltage from off to on. So there is a transition of voltage from from off to, if I may take this, to zero, isn't it? So this is during off state, and now you have the on state here. The voltage gradually reduced from the voltage off voltage into the zero voltage, and also have that also happens to the current. The current rise from 0 to the circuit current when the switch is on. Is it? So there is an overlap here between voltage and current. So that gives the instantaneous power P equals to VI. So instantaneous is at any instant you will multiply P V multiplied by I, that will produce the instantaneous power. Is it? So that give you the instantaneous power here. So if you take the area under the curve here, that will give you the energy. So if you integrate the power, the instantaneous power waveform here, you will get the energy. Okay, so now we're going to look at the derivation of the how to calculate for the switching losses. So during turn on and off, ideal switch requires zero transition, as on this case, zero transition. Voltage and current are switched instantaneously. But in real switch, due to non-idealities of power switches, the switching profile is as shown in figure 3.16. This one, 3. Alright, the switching losses occurs as a result of both voltage and current changing simultaneously during the switching period. The product of device voltage and current gives instantaneous power P dissipated in the device. The heat energy, omega W, that developed over the switching period is the integration of instantaneous power over time, as shown by the shaded area under the power curve. Okay, so now let's look at the derivation of average switching power loss. So this is the main switch, right? So this is the main switch, and this one is the out voltage of the circuit, and this is the current of the circuit. Right? So when the switch is off, so that current will flow through the diode here. Is that it? Right? When the voltage and therefore when this is short circuit, therefore the output the voltage across the switch will equals to VD. Is it? Can you see that? This is when the off, when the device is off, diode is on, so current will flow in that direction, and therefore this circuit will be short circuit, and this diode will be short circuit. Therefore this point will equal to that point, the terminal. So VT will be equals to VD during off state, but during on state, this is switch on and it become short circuit. Therefore the current will flow through here and the diode will be turned off, right? Therefore voltage across VT will be 0 and current will be IT equals to I naught. Right? So that's to explain the circuit operation. And now we're going to look at the transition of voltage and current. Okay, so let's start with this is the signal. This is the control signals to the switch. Control signals. This is off state and this on. So we trigger at this particular point here. We want to turn on the switch at this particular point, but ideally there is a small time delay. This is a small delay time here. We trigger the switch at this particular point. However, because of some non-linearity of the switch, it only turn on at this particular point. This is known as a delay time. Okay, don't worry about that. But after that, then we see the current start to rise. This is the current. Okay, so the current start to rise from 0 to the circuit level I naught. Okay, and the voltage only reduced to 0 when the current reach that level. When the current start to reach the I naught, the circuit current level, then the VD start to reduce. It doesn't happen here. It doesn't happen same times the current rise. It happens only when the current start to reach its circuit current. Okay, so VD start to reduce until, so ideally V on is 0, isn't it? So we can assume that this is 0, but practical there is some V on. But we just want to focus on the transition, the switching loss here and here, isn't it? Yeah? This is the switching loss, and that one actually is a forward conduction loss. This is during the circuit is on, the device is on. This is, but we're going to focus on this switching loss, and therefore we're going to consider that VD, V voltage VT here, as well as IT during that point. Okay, so this is the on time. Okay, and that also happens when, okay, so let me, this is off, this is on state, and this is when during the switch is off. Okay, so we have off state, on state, and off state. Right, so now this is where we want to switch off the device, but somehow there's a delay here. Don't worry about the delay here, we just want to focus on when the current start to reduce and the voltage start to increase. Okay, so when we want to switch off the device, we give a signal here, but it happens just after the delay time. Yeah, just after the delay time here, then we see that now during the turn off, we see the voltage start to increase first. The voltage from 0 level start to increase until it reach VD. Then we see that the current start to reduce to 0. Okay, so that is basically the profile of the voltage and current across the switch during the transition of from on to off and off to on. So if you look at further, if you multiply V and I, if you multiply V and I, you will get this triangle. This represents the instantaneous voltage. You see that triangle, as well as the turning off, and we see this triangle as well. Okay, so there are two triangles here. This is during turn on, and this is during turn off of the switch. Okay, so you get the power, and if you integrate to get the area under the curve, that will give you the energy. So this is known as a triangle. So you apply the triangle equation. So half multiplied by the height multiplied by the base, isn't it? So therefore half multiplied by, this is the height, and this is the base. Okay, so that gives you the energy during turn on, and during turn off you have half multiplied by VD I naught, again the height of this triangle, and then you multiply by DC off during turn off. Okay, so that gives you the energy of the switching loss. Okay, so refer to figure 3.1. You can read that. During on state, IT equals to I naught. Diode is open, used to reverse, the voltage has open option. So you read that. So I've already explained that to you. And then we have PT equals to VT IT. The TC on, the turn on time equals to TRI, TFV. Don't worry about that. And then finally, energy dissipated in the device during this turn on transition can be approximated using the triangle, because it's the area of the area under the curve. It's a triangle, so you apply the half multiplied by the height multiplied by the base, that gives you the half VDI on. And during turn off, you get the same equation for V energy, half VDI off, but now we have a TC off, the turn off time, and the total energy dissipated across the voltage, across the device will be V over WS, the switching loss, energy on, energy off. So you multiply that, So you get this on, this off. Since the power is the rate of doing work, the amount of energy transfer per unit will be omega W over Ts. Energy equals to power. Power equals to work divided by time, isn't it? Energy divided by time. So Ts is the period, and therefore you have Ws multiplied by Fs, the frequency of the device. Hence, the average switching power loss equals to Ps in the switch, which can be approximated. So the total power equals to half Vd I naught multiplied by the turn on time and plus turn off time multiplied by the frequency. So what can you say is that the switching loss heavily depends on the switching frequency. So the higher the frequency, the higher the power, is it? So if you operate the device at high frequency operation, you also need to look into to consider the power loss that occurs during that high frequency. Okay, so the average power loss is the sum of turn on and off the energy and multiplied by the switching frequency. When the switching frequency increases, switching losses also increases. This limits the usable frequency range of power switches unless proper heat removal mechanism is employed. So you have to make sure that you use a proper heat removal mechanism. Heat sink. Sometimes we have this fan. If you notice that your PC also has this fan, isn't it? The heat sink, the CPU fan. That actually the purpose is to remove the heat that produced by the components, especially the device or switching device in your circuits. All right, so this is an example. I hope you go through this. VDS is 600 volt, ID is 5 amps, so this is the voltage of the circuit, current of the circuit. Switching frequency of 1 kilohertz, 100 kilohertz, and you have a TC off and TC on equals to 100 nanoseconds. Calculate the total switching loss. So just apply that, then it gives you 30 watt. And therefore, if you increase switching frequency, then PSW, the total switching loss, also increase. Okay, right. Now next we have the safe operating area. Convenient method to summarize maximum values of current. Different devices have different SOA, safe operating area. So of course each of the device has its own current and voltage capability, but it doesn't mean that the voltage can work at that particular rating while you're having the same current. Sometimes it's misleading. The device specification, the design spec, it doesn't reflect the true performance, through the capability of the voltage and device of the voltage and current. So for example, in here you have a few, this is for one device. So this device can operate at 100 volt. Okay, let's see. Right, and with that current, when you operate at 100 millisecond, the period is 100 milliseconds, which is the low frequency. So if you go further up, if you increase the frequency, then you can see that 100 millisecond. Different devices have different for typical BGT. So it depends on the operation of the frequency of the voltage, the device. Then you can see that in different applications, different current voltage is applied for that particular. So this is known as safe operating area. And to avoid the switching loss, we need also to consider to use the snubber circuit. To use the snubber circuit, for example, you can read that this is known as a snubber, so that is to reduce the spike and to reduce the power loss. And we can also have the RCD snubbers. so you want to slow down. Instead of you have a high increase in the voltage, for example here you have a sharp increase of voltage, but if you apply the RCD snubbers, now your voltage is not increase suddenly increase with a high slope, but it's gradually increased, so that reduces the power loss. Okay, and finally you have this ideal versus practical switch. The differences between ideal switch can be summarized as in table 3.1, so you could compare between the two. For ideal switch, it blocks arbitrarily large forward and reverse voltage with zero current flow when off. Of course, the ideal switch, when it is in off state, this is off state. Okay, so this is during off state. So it blocks arbitrarily large forward and reverse voltage with zero current flow when off. This is during off state, and the voltage can be very high for ideal state, but in practical there's a finite blocking stage, finite blocking voltage, which is it depends on the device. It can block only 600 volt, 200 volt, depends on the switch, with small current flow. So during turn off, there's still a small current that flow, the leakage current. And then we have this during turn on. When the switch is on, it can conduct arbitrarily large current. Large current can flow with zero voltage drop, but from practical there is a finite current flow and depends on this device. So there is a limit of current flow, and of course there is a small voltage drop during turn on, and the switch from on and off vice versa instantaneously. So this is during the transition. Okay, so this is during transition. Okay, switch from on to off or vice versa instantaneous when triggered. It requires finite time to reach maximum. So we just see just now, we have seen just now that the voltage rise and also the current reduce. So there is a delay in time, isn't it? TC on, TC off, so that contributes to the power switching loss. And finally, very small power required from control source to trigger the switch. So ideal switch, you don't need the driver circuit in ideal switch, but of course in practical you need that driver circuit to trigger to turn on the switch. Okay, so I think that's all. Okay, right, thank you. So you can start to understand the start to remember, memorize of these things. Okay, there's a small calculations part in this chapter, only involve this basic power loss and probably calculation of the current. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.